Hi everyone, this is Yendong from Georgia Tech. And briefly introducing our work, Accelerate on-chip incremental learning with computing memory technology. Here's the outline of the presentation. I will first introduce the motivation of this work. Next, I will talk about the algorithm design for incremental learning, which is based on network expansion and partial retraining. Since the partial retraining introduced unbalanced workload, in section 3, a workload-aware hardware resources assignment protocol is proposed. Then the computing memory-based training architecture design is illustrated. Training accuracy and hardware performance evaluation are presented in section 5 and 6, respectively. The conclusions are drawn in section 7. The motivation for this work is that the DNN model needs to be adaptive to users' demands over time. For example, imagine there is a surveillance monitor using a DNN model for object detection. Initially, the DNN model is trained on the cloud, and it can detect the object classes in the training dataset. When it is deployed, the user may have its own object class of interest. Those data only appears on the working environment, and therefore is not available during the cloud training. In order to adapt the DNN model to those new classes, the training images for the new classes are collected over time, and the DNN model are incrementally trained to include those new classes. In this work, the incremental learning is defined as adding new classes into a pre-trained DNN model that initially supports some classes, which is termed as the base class. We assume that only part of the training images of the base class is available. The key challenge for incremental learning is a catastrophic forgetting. One solution is to retrain the selected weights in each layer. However, it's too fine-grained for computing memory technology. The other way is to increase the model capacity, which is coarse-grained and therefore is suitable for computing memory. In this work, we use network expansion to accommodate new classes. For each layer, the number of convolutional kernels is increased by delta k out to extract additional features. Therefore, the number of input channels is also increased. For the base kernels, it is expanded by 0 so that the output feature maps produced by the base kernels doesn't change. During the training, we only train the new kernels while the base kernels are frozen. A low precision training scheme is used with 8-bit weight activation gradients and 16-bit arrows. However, one issue with the partial training is the unbalanced workload during training. We divided the training process into 4 stages: the feed-forward, arrow calculation, gradient calculation, and weight update. Figure A is the weight mapping scheme for feed-forward and arrow calculation. Figure B is the weight mapping scheme for the gradient calculation. We use computing memory array that supports transposable array for feed-forward and arrow calculation, which is called the transposable array. We also use non-transposable computing memory array for gradient calculation. In the partial retraining, since we only retrain the new kernels, the workload for gradient calculation is small, which means the processing elements for the gradient calculation is underutilized. Based on the pipeline design, the pipeline stage time is the longest stage time among the feed-forward arrow calculation and the gradient calculation. Therefore, in our case, it is bottlenecked by the processing time of the feed-forward and arrow calculation stage, while the hardware resources for the gradient calculation is underutilized. We can assign more resources to feed-forward and arrow calculation to reduce the latency and therefore improve the throughput of the pipeline. To solve this issue, we propose a workload-aware resources assignment protocol. In the protocol, the basic idea is to first find the slowest stage among feed-forward arrow calculation and gradient calculation across all the layers, considering their workload, and then we assign hardware resources to the bottleneck layer to speed it up. It is assumed that the assignment is at the granularity of processing element. In the protocol, the first step is to identify the stage with the longest stage time and its bottleneck processing stage. Then, if there are sufficient processing elements available, we will assign more processing elements to this layer to speed it up, and therefore it is no longer the bottleneck in the pipeline. We repeat this process until all the PEs are assigned. And here's the training architecture design using computing memory technology. The figure A is a transposable array design. A 2-transistor, 1-resistor based memory cell design is used in the array. The multi-bit input feature map is input as single bit for multiple cycles, and therefore shift and add is used. The ADC is implemented with multi-level current mode sense amplifier to convert the partial sum current to digital values. During the feed-forward stage, the input feature maps are applied to the word line along the horizontal direction. The partial sum current along the vertical bit line is sensed by the ADC. During the arrow calculation stage, the arrows from the deeper layer is input as a word line along the vertical direction. For a transposed read, the source line is connected to the ADC. In the non-transposable array, we use the conventional one transistor, 1-resistor bit cell design. And the array size is assumed to be 128 by 128 for both transposable array and the non-transposable array. And the figure B is the processing elements design. There are 2 types of processing element. One with transposable array for feed-forward and arrow calculation, while the other with non-transposable array for the gradient calculation. Each PE contains 9 memory arrays, since most of the kernels are 3 by 3. The input feature maps and the output feature maps will be stored into the SRAM buffer. The multiple PEs are grouped in a tile. There are 32 tiles. There are 32 PEs in a tile. In each tile, we have 512 kilobyte SRAM input buffer to store the input or output data, such as the partial sum, activation, arrow, and gradient. There are also special special function units such as ReLU and max pool in each tile. As a hardware resources assignment protocol may assign a regular number of processing elements to each layer, a flexible interconnect design strategy is utilized for the processing elements and the tile level communication. In each tile, the 128-bit input bus is connected to each array to deliver the input feature map. To reduce the partial sum from the arrays, a routing switch with adder is used, which adds up the partial sum when they are propagating along the interconnect. And the microarchitecture design of the routing switch is shown as below. In the tile level, a binary tree-based interconnect is used to deliver the input feature map and collect the partial sum. Similar idea of on-the-fly partial sum reduction is adopted to alleviate the link bandwidth requirement. And here's the microarchitecture of the switch. Since the output partial sum or PEs are of different bit weights, a shift register is needed to shift the partial sum of higher bit weights. A bypass link is also included if the partial sum cannot be added up. The downstream network for the input feature map delivery is based on regular switch, which can multicast the input to a group of PEs if they are receiving the same input feature map. A mesh-based network with routers is used for the communication between tiles. There are 32 tiles in our design. The intermediate data will be sent to off-chip DRAM if the on-chip buffer is not enough to close in. LPDDR4 is assumed for the DRAM interface, which is commonly used in the edge accelerator design. To evaluate the training accuracy, ResNet 18 and VGG 16 for CFR 100 dataset are used in our work. The network expansion delta K out is described as a percentage of the number of output channels in the original DNN model. The initial DNN model is trained with a full training data set of the first 50, 80, and 90 classes, respectively. Since the capacity of the DNN model is reduced for less number of classes, the K-out is also reduced correspondingly. Two scenarios, the single-step learning and multi-step learning are considered. For the single-step learning, the new classes are learned for one time. For multi-step learning, the DNN model is expanded and 10 new classes are learned at each step. In the experiment, we consider different expansion factor data K-out and different number of training images for the base classes. And here are the results. For the single-step learning, a good training accuracy is achieved even with the device conductance variation. For single-step learning with 90 or 80 initial classes, the network expansion factor data K-out and the number of training images for base class have very small impact. For single-step learning with 50 base classes, more significant accuracy improvement is observed with a larger network expansion factor delta K-out. For example, when delta K-out is 75%, the accuracy is about 0.7% higher than delta K-out equals to 50%. For multi-step learning with 80 and 50 base classes, the final accuracy with 100 classes is about 1.8% and 6.7% lower than those obtained with single-step learning, respectively. By properly tuning the hyperparameters, the impact of base image number can be minimized for both cases. From the results, the training accuracy can be maintained with part of the training images of the base class. 150 images of the base class is sufficient to get a good accuracy. In the hardware design, we use STT-MRAM as a weight cell due to its low write energy and good endurance. Besides, commercial foundries have started to provide the process for 22 nanometer STT-MRAM. The device parameters are listed in Table 1. The hardware performance evaluation is based on the modified NeuroSim simulator. It generates the computing memory array performance using the listed device parameter as the input. The clock frequency is 500 megahertz by analyzing the critical path delay in the computing memory array. To evaluate the effectiveness of the workload-aware hardware resources assignment protocol, a baseline design that only uses a transposable array for feed-forward error calculation, while non-transposable arrays are fully utilized for gradient calculation, is included for comparison. 2.3 times to 4.2 times throughput improvement is achieved for the tasks with a small expansion. This is attributed to the balanced processing time between the feed-forward error calculation and the gradient calculation in our design. The benefits becomes less significant when the network expansion delta K-out becomes larger due to the higher memory utilization. On average, 2.2 times and 2 times throughput improvement is obtained for ResNet 18 and VGG 16, respectively. The average energy efficiency of our design is 4.1 TOPS per watt over different learning tasks and the different DNN models, which is 3.7 times to 28.7 times higher than the computing memory baseline designs using RAM. It can be attributed to the high write energy for the RAM. The area efficiency of our design is lower than pipe layer because STT-MRAM is only 1 bit per cell. The RAM in pipe layer is assumed to be 4 bit per cell. Compared with CMOS ASIC-based accelerators, our design achieves 2.1 times and 2.9 times higher energy efficiency than the edge TPU and edge GPU respectively. To summarize our work, we propose the STT-MRAM-based DNN accelerator for on-chip incremental learning. A hardware-software co-design approach is adopted for the design. On the algorithm side, network expansion-based low-precision training algorithm is used for incremental learning. On the hardware side, hardware resources assignment protocol is proposed to improve the throughput. A good hardware performance is achieved in terms of the TOPS per watt. This is all about my presentation today. If you are interested in this work and would like to get more information, please take a look at this paper. Thank you for your listening.